All right. Good afternoon, everyone. So this talk is about statistics in fMRI. So statistics basically deals with data. So you build a model first, then the model usually reflects the current knowledge about the field you want to study. Then you want to learn something from data. So since fMRI involves a lot of data, so it covers a lot of statistic aspects. So this is the layout of the talk. First, we're going to go through a little bit background and about some statistical basics. Then we move on to a couple of aspects that are especially related to fMRI. First, we need to talk about the experiment design because that's really crucial to fMRI, even though most people probably may not realize that. So how do we design experiment? Design an effective experiment, then try to get what you want to get. So that's the second part. The third part is the modeling part. In fMRI, usually we have deal with the typical pipeline. We deal with the two levels. The first level, you analyze the data for each individual subject. Then you move on to the group level. So those are the two aspects for the modeling part. Then lastly, we're going to, if we still have time, talk about a few limitations about the current modeling approaches in fMRI. So what is statistics? So the word statistics, probably about 250 years old. I mean, it started with a German word. Originally, the word statistics basically is related to the word state and status. Basically, that shows something about the current understanding about something based on the data. So with data, we usually have pretty noisy, especially for fMRI. So there's a noise part. There's a variation. Variation, we know the word is not uniform, right? So for fMRI, for example, we look at the difference between genders, right? Males versus females. So that's variation. Or we want to look at two different emotional states. For example, something happy or something versus something sad. So those two states, usually we expect to see something difference between the two emotional states in the brain, some brain regions. So that's variation. But in addition to that kind of variation, we also need to keep in mind there are not enough noise in the fMRI data. Why do we have noise? Well, the big part of it is because our knowledge is pretty limited. We don't fully understand what exactly what kind of components embedded in the fMRI signal. We don't fully understand. The current knowledge probably is we can only understand about 30 to 50% in the signal. So the big chunk of the stuff in the fMRI data, we just bundle them, call it noise. That doesn't mean it's real noise. It can be something really we just don't understand. We cannot exactly model them, those components. So how do we deal with that kind of a noise situation? That's some part we need to solve it through a cumulative process. So for typical studies owners, there are 4 steps. First, you design the experiment because there are 2 types of data. One is called observational data. That's you don't need to do anything. You just passively sit in there and the data will come in. That's called observational data. But for fMRI, usually it's not, we don't just observe. We need to design the experiment, very meticulously design experiment. Like you want to look at happy versus sad, those 2 emotional states. You have to design experiments to show the subjects what kind of emotional images or sound you want to show the subjects. You have to design very effectively. Then you can squeeze something out of the data. So that's called experimental design. So once you design experiment, then you recruit subjects, then you collect the data. Once the data is available, you move to the next stage. You build your model, then try to see if that model tells you something. If that model is what you expected, if not, then you may change your model, right? So maybe build a slightly better model. So they go through multiple process iterations of model building and comparison. Then you want to say something about the data you collected. So that at that stage you may, make some conclusion. Then the last step is write up, right? So publish the result, or make a prediction about some, for example, emotional states. So statistics, well, humans to some extent are, everybody is a statistician to some extent. So for example, currently we have the lottery, right? So the Powerball. So when you buy a lottery ticket, you think about, is it worth buying or not, right? So that's, if it boils down to a statistical question in the sense that how much money you pay versus how much you could gain, right? The cost versus the gain. That calculation, if you are rational, probably it's not a good idea to buy a lottery ticket. But the human psychology is that you tend to think about if I win, right? So win the big chunk of money. So that part, that psychology part is pushes everybody, most people to buy a ticket, lottery ticket. So and a few other examples, like for example, the second one, they are, for example, in the US, how many people every year die because of snake bites, right? Because of snake problem? 15, right? How about flights, air crashes? About 200. How about because car accidents? That's 40,000. But that's a pure number, right? So of course that's average. Every year it fluctuates. But in terms of human psychology or emotion, that the order of the number of death is the opposite, right? So most people are afraid of snakes instead of flying. So the order is totally reversed. But that's because evolution, right? So that's because even before human occurred, it emerged. It's even the animals, they're afraid of snakes, right? So that's basically coded in the genes. So the third example is, suppose I flip a coin 5 times. I get it all the 5 times I get heads. So what's the chance you to get a head again the next time, the 6th flip? Well, this is easy, right? So everybody knows this. Assume that the coin is nothing. It's a typical coin. Then what's the chance you to get a head next time? 50%. Yeah, it's because it's unless there's something wrong. It's a fake coin in that case. So that's called the independence, right? So but this is the easy one. But how about? Oops, I don't want to show that result. How about this one? We know the HIV in the whole population, that is about 1%. So 1 out of 1,000 people, that's the ratio. Also, we know that it's based on previous statistics shows that if a person is blood test, it shows HIV positive, but if the likelihood that test is false positive, that means the test itself is positive, but that person does not carry the virus. That called false positive, right? That means low virus in the blood, but the test shows positive. That's called false positive. That's 5%, right? So that's when we do fMRI. Also, we have that concept of a false positive. Nothing going on in the brain, no activation, but by pure chance, you could have detect some activation based on your model. So that's called a false positive. Suppose it's 5%. Then the power of the test, that blood test, is roughly 100%. What does that mean? What is power? That power means the person in reality does have the virus, but the test successfully detected that. That shows the robustness of the test. So it's pretty much sure if the person does have virus, the test will catch it. So that's called the power. So that's basically the information you have. Now we have a person, his blood test comes out as positive. So what's the likelihood that person does carry the virus? Can you give a guess? Just give me a wild guess. Whatever you feel would be the likelihood, the probability. So the test itself now is positive. What's the chance the person does carry the virus? 90%? 50%? Just give me a wild guess. You're fainting. Nobody is willing to give me an answer. I mean, just 5%? 75. Yeah. All right. Any other guesses? 5%? No more? 25. Okay. 5, 25, 75. No more? All right. Let's say the real answer. 2%. Well, this formula is the famous one. It's called a Bayes. It's named after the British statistician. He came up with this formula to calculate this called the posterior probability about 250 years ago. So basically this is called a prior information. So that's basically that's before this person gets tested. We know that on average, everybody has the chance. If just on average is 1 out of 1,000. That's called the prior information, right? So ignore any other potential information like lifestyle, or symptoms. So we just based on the population information, that's called the prior information, without knowing anything else, just based on the previous statistic. So 1 out of 1,000, that's prior information. Now we have some, it's called a likelihood. So those two numbers, 5% versus 100%. False positive, that means nothing going on, no virus. But the test itself, no virus, maybe we made a mistake. Something came up either 5 out of 100 case. The power, if the person does carry the virus, then the test will catch it. So that's pretty robust. But you go through this formula, you end up, so basically you have the prior information, you have the likelihood information, plus now we have the new data comes in. The new data is this person the test result does show positive. That's the new data I have. So now we update our knowledge based on this formula. It is updated. It's 2%. Before it was 0.1%, now it's 2%. So it's 20 times higher than the population information. This sounds like a little bit counterintuitive, right? But in reality, of course, this is when the doctor, when the diagnose, not just based this one piece of information, we have other information, like lifestyle, as I mentioned, lifestyle, other symptoms, right? So the reason the person wants to have this test must have some other information available. But this says something about the cumulative process, the information we have. So it's the reason, you think about it is to start with, the information is the rate is already low, extremely low, right? So that's one reason. Of course, you have to understand this base thinking or philosophy. In fMRI, this kind of is called the Bayesian, right? Now it's called the Bayesian approach. This approach is does not get used much in fMRI, but hopefully in the future, this will probably tends to get more and more usage, because this does, as probably I will show on the next slide, and in real life, we do use this kind of Bayesian thinking in our real life. For example, this is a little bit in our daily life. Back in history, in Bible, they talk about the sensors. That's basically you get some information about the number, the population size, right? But how about the stereotype? There are a lot of stereotypes in our real life. That is basically it's a statistic thinking. Why? When we talk about, for example, one ethnic group, some general impression about one group of people or gender is that people just think about the average, the mean, or the median, right? So this group, the typical impression about this group in average, but they try to summarize something about the one specific group, about something. That summarization is it's too simplified. That's because you focus on the average or you focus on the median. But when we talk about each individuals that we need to keep in mind when we talk about statistics. In addition to mean or average or a median, there's a variance, right? So the variance can be huge or can be small. That depends on the group or the data. So that's why we have the stereotype, because it's economical to keep. People tend to forget about the variance part. When you walk in stairs, especially walking downstairs, right? That's a Bayesian thinking in the sense that each step you have some expectation, right? So if sometimes you made a mistake, you think there's a step there, but no, there's no more steps. Now your expectation and the reality, there's a discrepancy that you know when you walk downstairs. That experience that's not too bad compared to the other scenario. There is a step. You thought there was no more steps, right? That would be a big problem. So that is a Bayesian part, actually. You thought your prior information is no more steps, but in reality there's still step there. So that's a discrepancy. Bayesian. Naturally, we already talked about that. That's basically called expectation or expected mean versus the cost. That's the basic decision theory part. In other aspect in our real life is that the insurance, right? So that's basically risk management. We pay something, but we want to avoid the worst scenario. But to get that to work, we have to pay more than what we usually the average cost, right? So if you are a driver that is better than average, then probably it's not a good idea to buy insurance, right? But if you are below average, of course, probably that probably is a good idea because, here the tricky part. Complicated part is not just the average. Also, we have to pay the insurance company to manage the process. So that's the insurance part. Then there are other part like airbags, ABS, other security system, right? So they are also, the cost is a little bit higher than what they average, right? So the airbags will have to spend way more. Probably most cars, probably the airbags is in the end is basically a waste. But the issue is that whenever something dramatic happens, then that can save life. So we invest a lot of money just simply to avoid the worst scenario. So that's a little bit probably too far away from the fMRI. So now let's come back to the fMRI part. So remember, we have typical 4 steps when we do statistics. The first step, we design experiment, then collect the data. So that's the first step before we even start the modeling part. So in fMRI, when we design experiment, there are typically 3 categories. The first one is called a task-based. Well, why do we do task-based? That's because we want to understand the human brains, right? So like we understand the emotion, which regions in the brain are involved in emotional response. So that's a task, specific task. So we have to make it concrete. So we need to design experiment, show some images that with some emotion expression, right? So that's called a task-based. The second category is called a resting state. Resting state, that means no tasks. That means you ask the subject to lie in the scanner, don't do anything. Well, that's hard. You lie in the scanner, don't do anything, that's impossible. Your brain is always daydreaming or think about something, right? But at least those specific tasks are just a drifting effect. So the reason people use this kind of data is trying to understand the human, that kind of drifting effect. That's called, for example, one possibility is look at the so-called default mode network. So the brain is doing something, but that doing something is largely comes from the external task, but something more about the internal. So that's why people are interested in this kind of scanning recent state. So both those states are still sort of a little bit, people call it a little bit considered far-fetched, especially for the task-based. You show some people, the subject in the scanner, some images, right? So those images are not, usually it's a little bit artificial, right? Far away from the real life. So they consider that it's not a real life experience. So that's why there's a third category, it's called naturalistic scanning. So in that case, the typical ones are you ask the subject to watch a movie or listen to music or listen to some speech. So that's closer, may not be exactly real life, at least closer to the task-based experiment. So in that case, then you can say something, I mean, it's more realistic. So those are three categories. So the early days, people, I mean, little bit way back, more than 20 years ago, when I first started, people, I mean, usually use simple tasks, right? Like push buttons, that's the simple ones, to say something in the motor control region in the brain. So then for those, whatever those, one of the three typical currently available designs, there are some parameters when you design experiment you need to take into consideration. So for example, you scan for how long, right? So for a few minutes or half an hour or 1 hour. So how long, it depends on the nature of the experiment, of course. And also that about the data, amount of data you want to acquire. So there's a concept of number of time points. The time points for fMRI, typically you scan the whole brain, then within some short period of time, like for example, 1 second, then you scan take a second snapshot of the brain. That's a second. The interval between the two three-dimensional volume is called a TR. It's called a time of repetition. It's called TR. So that the TR length that shows the interval. But how many data points? That people call it how many number of TRs. So that's, of course, from statistic perspective, the more the data, the better, right? It contains more information. But that more, how much more? So that proportionality, roughly speaking, is proportional to the square root of the number of time points. So it's not exactly proportional, but proportional to the square root. Well, square root relationship is not linear. It tempers off. I mean, it's still, you get more data, the better, but that betterness, the better part is not, after some time point, is not as much as the initial few data points. So that's the number of time points. Then there's the gap between two volumes. Typically, it's 2 seconds nowadays. Well, why it's 2 seconds? That's because more about the limitation of the hardware. So like 3D, especially for 3 Tesla scanners, usually it's 2 seconds. But you can get it down to 1 second or even shorter. But to do that, you have to sacrifice the coverage of the brain volume. So you have to narrow down to some regions to sacrifice that. So that's with a high strength field, like 70 or even 13 point something, that's high magnitude scanners. The TR can get it down to even lower, but that's not typical. So 3D scanners are still the typical ones we deal with. So there are other, in addition to those scanning parameters, there are also for your own experiment, you need to think about how many tasks. For example, emotion, you only have happy, sad, or maybe neutral. So those are 3 conditions, right? So that's one variable you need to think about. Then do you also need to think about between males versus females, right? So that's another variable you need to compare 2 groups. So that's one aspect. So the experiment itself, the tasks itself, themselves, also the subject itself, right? You need to have, for example, autistic group versus control group. In addition to that, you also need to think about how many number of subjects you need to recruit, right? So that's another factor you need to take into consideration. Of course, the more the better, but then the more you have to pay the cost, right? The cost of, pay the subjects to come to scan and analyze, time consumption, right? So that's the more data, the better, but also you have to pay money and pay time to have more data. So that's the last aspect of experiment design is about once we have the data. This is still an experiment design stage, but you still need to think about the modeling part. That's because that have impact about how do you design those. Think about those parameters, the number of subjects. The modeling part for fMRI, once you have the data available, suppose you already pre-process the data, then for each subject, now you want to identify the regions in the brain that you can confidently say, those regions are activated. How can we do that? We'll have the data at each voxel. The data contains the information about the brain response. That response, how do we identify the response? Typically, the popular approach is, remember fMRI signal is called bold signal. That says something about the brain response, but that brain response is an indirect measure about the brain response. It's not a direct measurement. That's because the scanner can only detect the blood flow. The reason the blood flows in the brain, that's we think because a specific brain region is doing something, it needs blood. Why it needs blood? It needs oxygen, needs nutrients, right? To the neurons, they immediately once that region, the neurons is doing something, it needs oxygen and the nutrients immediately. So that's why the blood flow is suddenly quicker. So the scanner can detect the blood flow, but the scanner cannot detect the neuronal activities. So that's why it's indirect measurement about the brain response. So the brain response, the neuron response is quick, right? It's at the microsecond level. But the blood flow is way much slower. It's at the second level, seconds. So in this curve I'm showing here, it's called a bold signal. That shows the blood flow. So here at the beginning, suppose I ask the subject in the scanner to push button. Suppose in the motor control, it responds quickly, right? Within, for example, 150 milliseconds, the subject pushed the button. That short period of time, then in the scanner, we would presumably say something like this. So the x-axis is in seconds. So this is from 0 to, for example, 16 seconds. So the blood flow, the signal, bold signal is goes up slowly, reach to the peak, then even slow. The recovery part is even much slower. So that's called the bold signal response. That response, we don't, theoretically speaking, we don't know the exact mechanics, the mechanism. So, but people approximate that with different mathematical function. For example, here's one. That function is called gamma variate. That function, so the x-axis is t, that's time. So it's expressed like this. So there are two numbers here. So there's the exponential part here. There's a scaling part here. So those two numbers, do they mean something? Well, maybe, but in reality, no, they don't mean anything. People just simply use this mathematical formula to approximate the Boltzmann response. They don't mean anything at all. Unlike in physics, we have gravitational constant, right? Speed of light. Those numbers, they have specific meaning, right? And they are usually very accurate. Here, those two numbers don't mean anything. They just it's a convenient numbers. People to use that. Oh, we use this curve to match the Boltzmann signal. It works roughly okay. So that shows how much we understand about the signal from the scanner. So that's basically one called gamma variety. Then the people have a couple of other options, but in the software fMRI, which I work with, that's the formula. But in other software package, for example, SPM and FSL, they use a slightly different curve. So but in the end, it boils down to pretty much similar. It's like this typical. Whenever you see in the signal something like this, that's a typical Boltzmann response. How is the approximation? That approximation is roughly okay, but later on we'll come back to this issue. So you make that assumption. You assume everywhere in the brain it responds like that. I mean, that basically says the shape. But in the magnitude, the amplitude is each brain depends on what tasks, depends on what brain region. So it varies. So the typical strategy is we use that curve as a ruler to measure in the signal you collected from the scanner. Use that ruler, this is the ruler, to measure that. So if there's something similar like this shape, then we find out the scaling factor, right? So some brain region may be higher than this, other region may be slower. So that is scaling factor. We use that scaling factor as the brain response measurement. So if it's one brain region is higher, then that scaling factor, we see that's our brain response. That brain response, that measurement, we call it percent single change. Percent single change relative to the, if nothing going on in the brain, there's a baseline. So when the brain does respond, that's a little bit higher than the baseline. That higher part is tiny. Usually it's about 1%, sometimes even smaller. Could be higher. The highest, it could reach 2% or 3%. That's pretty rare. Like motor control, you could reach 2 or 3%. But most other brain regions, like amygdala, those emotional stuff, usually it's less than 1%. So that's the signal is pretty weak. So this approach, I call it fixed shape. That's because you assume that's the response curve. But that assumption usually it's not so accurate. But people do it anyway. That's because, first of all, we don't know much about the wave response. Second of all, this is the easiest approach. We just use that as our ruler to measure whatever in the signal. So that's the simplest approach. There are two other approaches. For example, the third approach, we don't make any assumption. We just, later on we'll talk about details. So this is, we estimate the shape and estimate the response. So there's in between, there's some little bit of wiggle room to allow you to change the shape a little bit. That's the second approach. We'll come back to this point later. So let's talk about the individual subject. Then the group, then we'll talk about how many number of subjects you need to recruit, right? So that's usually nowadays probably you want 20 or more. That depends on the specific experiment, but we'll come back later. We'll talk about the group analysis. So that's the design part. So once you design experiment, you scan the subjects, now you have the data. How to analyze it? To analyze it, we typically, nowadays, we split into two steps. Well, first of all, you have to clean up the data a little bit. That's called pre-processing, which we're not going to talk about here. That's basically to make the data, to standardize it, calibrate it a little bit. Then in the end, we have the data available to analyze. So how to analyze? So suppose we recruit 20 subjects. So now we analyze each subject separately. So 20 subjects, we do 20 separate analyses. Then get the brain activation measurement at every region, every voxel in the brain. So that's called the individual subject analysis. Once you are done with that, we go to group analysis. Why do we need the group analysis? That's because we're doing science. Science, we don't focus on individual subject. We want to say something about the whole group, whole population, or want to say something about the group comparison. Is there any brain response difference between males versus females? Any differences between artistic group versus control group, right? So we want to say something about the whole population or group comparison. So that's the goal. So when we do something, we want to say something more general, something more generic. So that's the second step. Ideally, we don't want to split into steps. We want to, suppose 20 subjects, we put all the 20 subjects data together, one analysis, ideally. But we don't do that simply because two reasons. First reason, that's people, in early days, people start that way because fMRI started probably the first time just one subject. But the second reason, more important nowadays, is because the computation power is not there yet. We cannot handle the amount of memory and the computation time. We cannot do it that way yet. But hopefully in the future, for example, 10 years from now on, probably at some point, we will switch to that approach, which we analyze just one step. That approach is better in the sense we don't have to split in two steps, not just from a logistic reason, but from a statistical, from modeling perspective. It's better to just do it everything with one model to one step from modeling perspective, not the logistic reason. So, but now this, my talk is focused on the current state. So let's talk about the current focus. So when you have each individual subject, we need somehow to find out the brain response, right, to a specific task. That approach is basically we need to find out the signal, the components in the signal. So the fMRI signal, we partition into three components. The part of we don't care about, but we have to model it. That's called the effects of low interest. Then the stuff we are interested, that's like a happy versus sad. We care about those two effects. That's the part we want to pull out from the data. The third part is noise. Noise basically shows that's the limitation about our knowledge. Anything we don't know about it, we call it noise. So noise, we don't have much to talk about. That's just limitation for our knowledge. Effects of low interest, that's basically, first of all, even though you put in something, a dummy, right? So nothing in the scanner you scan, you still get some data and plus noise. That's called a baseline. So the scanner does have some signal baseline. That's usually the value is probably between 1,000 to 3,000. That's called baseline. There's a flat line, or maybe there's some drift effect. So in addition to baseline, you may have slow drift. Why do you have slow drift? Well, there are probably two or more reasons I have drift. For human, in the scanner, especially the first time if you get it scanned, you're probably a little bit nervous, right? So nervous, you feel, heartbeat is faster, blood flow, breathing is faster, especially at the first couple of minutes. That have some impact on the both signal. So that drift. So later on, after a few minutes, this not too scary, right? So you come down, then heartbeat is stabilized. So is your breathing. So that may cause some drifting effect. So that nervousness. So that's one reason, the slow drift. The second reason for slow drift is the scanner itself. They may have some thermal fluctuation, that drift, plus other effects which we don't know. There's have that slow drift part. Then the third others, one possibility is the head motion. I mean, when I'm in the scanner, probably after a while, maybe a face feel a little bit itchy. I want to scratch it, right? So, or you may want to swallow, right, a little bit. So that may cause some head motion, or if the task itself can also cause head motion. For example, if there's a speech study, the subject needs to talk, right, to say something, or even push a button, that may cause a little bit jerky motion in the head motion part. So those components are typically effects of low interest. So in the model, we need to deal with of those part, right? So, but the model part, I assume everybody here is familiar with the basic modeling approach with regression. You learn that in every statistics course, right? So the model, that model basically, that's our signal for fMRI. So we have, that's the baseline. Baseline basically is the intercept. Then we have those regressors. The regressors are, a better term probably is called the explanatory variables. We want to use those variables to search for the pattern in the signal, right? So all the stuff we don't care about, but we have to model them to explain them. So like the baseline is already here. The drift effect, we can put it here, right? So the task effects like happy, sad are also here. So the third component, that's the noise part. So that's our regression model. So the I, that's just the time points. For fMRI, it's different from the typical regression. Like typical regression will have height versus weight, right? So that's the I is usually it's not the time, it's more about the individual subjects. But for fMRI at the individual subject level, we'll have this time series because they're equally spaced. It's called a time series. So usually, if you are familiar with fMRI, basically in the end we write our model like this: y equals this at x. That's x. In fMRI we call design matrix because you design experiment, you have total control that matrix. So those regressors, how you put it at which moment you ask the subject to do something, that moment, that time, that information is embedded in those components. So that's totally under your control, the X design matrix, right? So again, this is a design experiment. It's not an observational study. So that's why in fMRI we call design matrix. The Y is the data you have. So in the end, what we care about is those beta. Those beta is the vector column. It's one column. So we want to say something about the data. So this is the typical regression, right? So for example, about 100 years ago, Charles Darwin's cousin, Francis Galton, came up with this idea about the height versus weight, or parents, next generation's height versus the parents' height. So you can use that straight line to approximate the relationship. But that's not exactly what we are doing. In fMRI, what our regressor is this width curve. We assume that's the signal we expect to see from the scanner. But the whale signal, the black one, is very noisy, right? So we use that width curve to search to see if we can find such a pattern in the signal. If we do, then we come up with the estimated beta value. If we don't, the beta is close to 0, right? So that's basically the goal. We find the beta value. Then how reliable is that beta? Then now we can say something about the brain response. So that's our goal. So we have this model, right? The model we have, that's data we have. That's the design matrix. We solve the beta. So solve the system. It's called the least square, right? You already learned this, right? That's a statistic. So then you do a bunch of tests. Suppose you say, is this brain region activated or not under the set condition? You solve the beta, you get the beta, right? So this is the strange part of a statistical analysis. We pretend nothing going on, right? So beta is 0. you pretend. We put a straw man like that, but nobody's care about this hypothesis. In the end, you want to reject. You want the opposite of this. But the traditional statistics starts with this concept of null hypothesis. Pretend nothing going on. So then you come up with some statistic, something that measure the discrepancy of your data versus this null hypothesis. For example, if a T statistic, that T statistic is huge, that shows it's so discrepant. So the discrepancy is so huge between the data you have versus null hypothesis. Now you sort of have some confidence to say, there is something going on. We can reject the null hypothesis. So you can identify the brain region specific response into this one condition, or you can compare two conditions, happy versus sad. So you use that test to identify the brain region which maybe respond more to happy than sad, or the other way around. So you do such a contrast instead of like this, right? So this is the contrast test, or you can do something more complicated. So that's the various different kind of tests you can run. But that's the typical individual subject analysis. So I'm going to skip this. But I just want to keep in mind the fMRI signal, there are three components. So the stuff you are not interested in, but you need to take care of it. So that's the baseline part. There's a slow drift. There's other stuff like head motion or some outlier you want to take it out. So those are we bundle them as effects of low interest. The red part is what usually we care about. That's the part you design experiment, the purpose you design experiment. So those betas you want to pay attention to. The last part is the noise. So that's the typical fMRI analysis at the individual level. So we talk about the curve itself, right? So you make assumption about the response curve. Occasionally, there's some called an undershoot. So when the curve reaches the peak, then recovers, but it over recovers. It goes under. It's called deactivation. So that's called undershoot. Then slowly recovers to the baseline. So there are different. That's in SPM and FSL they use this kind of a curve to model the hemodynamic response. So here, when you say this kind of curve, that means it's just we assume the task itself lasts pretty short of period of time, like this, 2 seconds or less. That's called the event-related design. So in that case, we assume the curve is just like this. But sometimes people design experiment that each trial, each task may last more than 2 seconds. For example, in this 10 seconds, it's not like the curve anymore. That's because you can sort of conceptualize this as many individual instantaneous multiple events. You just accumulate the effect of the previous curve I showed you. So that's, mathematically speaking, that's called a convolution. Basically, you add up those individual curves. So you don't say that they are shape, that the typical both response anymore. That's because it's the summation of those that convolution effect. So this is called a block design. So here is just this animation shows you all have 3 individual events. First, we have this black one instantaneous effect. We have this blue curve. The second one, we have this red curve. So after 3 seconds, we have the third curve, that's the green one. So in the end, in the signal you detect from the scanner, you don't say those 3 individual curves. You only say the accumulated effects, right? So you only have one curve signal like this on the right-hand side. So that's the part when you do modeling, you have to add up those 3 curves. That addition summation is called the convolution part. So that's when you create a regressor or experiment variable that basically involves this mathematical concept of a convolution. basically convolution is sort of like a multiplication. So you add up those individual curves. So that's most of the time people nowadays use it, but that's not really accurate in the sense that you make a really strong assumption. You assume that the curve is the same for everybody, regardless males or females, regardless as a typical person or versus a diseased person, or regardless what the brain region. That shape is always like that. That's the assumption. So it's an idealized situation. In reality, of course, the brain region from one region to the next region varies. That response curve, the shape varies. From there are personal individual variation too. So people use this approach, this idealized approach, simply because it's easier, much easier. But in reality, I mean, we know there are a lot of variations. So ideally, probably there is a better approach. People don't use it. That's because it's more difficult. You have to do, as a person, you analyze the data, you need to do more work. You need to understand more. So it's more challenging, but it doesn't mean there's no approach available. So there is. That approach is you don't make assumption about the curve. You don't put a constraint about the curve. Instead, you just put a ruler at multiple time points. That ruler is just like a height. Say this is 1% signal change. So you go to each time points, you measure the signal, say, oh, at this time point, this response is shorter than 91%. Okay, let's say 0.1%. Next time point is 0.3%. So you walk through every time point. You use that ruler to measure it, the tape measure. So in the end, unlike the before, you have one curve, in the end, one task, you get one beta value. That one beta value is the scaling factor, says something about the brain response. But in this case, each task, you end up with several betas. Those several betas basically shows you so for example here, from this stimulus, suppose you push a button. So now I'm going to measure from this point. At that moment, we don't expect any brain response, 0. Here, we put our ruler there, we get our beta 1. Next time point, beta 2. So in the end, we'll have those multiple betas. Well, we connect those multiple betas. So we end up with those connected. We connect those beta value. We end up with this shape. That shape gives us information about the shape, and the brain response magnitude too, because each time point has the amplitude information. So this approach, at least theoretically speaking, is better, is more accurate because it estimates the shape as well as the amplitude. So this approach is usually it's better, but people don't use it. That's because the challenging part for the investigator. You have to understand more, do more work. But from a scientific perspective, it is better and probably usually it's more sensitive, and you tend to detect more. And I mean, we did try this on one specific data set. Sometimes even have undershoot at the beginning. So here you have the stimulus onset, then you may see undershoot at the beginning, also sometimes undershoot at the end. So those sort of subtleties, shape subtleties, tells you something about the brain response. The idealized approach would not work. So those are the two extremes. But of course, there are some other approaches. So that's now let's move to the group level. Group level basically, it's suppose you analyze the individual subject analysis, right? So you end up with suppose you're happy, sad, you end up with 2 betas. If you just use the simple approach you make the assumption about the hemodynamic response, you end up with 2 betas. So go to group level, you only say something about the whole population, right? So what it would be the model at the group level? So you just one group of subjects, you have two conditions, happy versus sad. That's a simple model. That model is called a paired t-test, right? So you compare two conditions. That's called a paired t-test. Suppose you have two groups, males versus females. You want to compare the two groups in terms of a happy response. So that's called two-sample t-test, right? So everybody learned that already, right? So those are the two simple cases. But you could have more sophisticated scenarios. Like here, suppose we have two groups, patient group versus control group. Two groups, three conditions, positive, negative, and neutral, happy side and neutral, three conditions. Then you may have, each group have 15 subjects. Then you may also consider age as a covariant. So that's nowadays in fMRI is probably typical. That's probably called ANCOVA, right? So that's ANCOVA model. But even for that model, it's a lot simple for fMRI. But if we learned the software package like SAS or SPSS, probably this is not hard to analyze. But for fMRI, actually, this kind of ANCOVA is very challenging for fMRI. It's still usually it's not done correctly in fMRI. Unfortunately, that's because not every software package implements this sort of model correctly. But I need to be digress. But so in FNE, this is modeled as a multivariate model, pretty much like a SAS and SPSS or R. So that's use a multivariate modeling approach. So I'm going to skip the details. So that's basically fMRI and the task related. Then there's I mentioned at the beginning, there's a third type. There's a Wilson state, which there's not much modeling other than correlation analysis. The third type is called inter-subject correlation. That's for the naturalistic scanning, like watching movie, listen to music, or listen to speech, right? So that's more close to real-life experience. You put a subject in the scanner, watch a movie, for example, Forrest Gump, watch the movie for 3 hours. You have the data. Then how do you analyze it? That's called the inter-subject correlation because there's no specific tasks involved in the signal. But you do have, different scenes or continuous situation in the movie. So where there's no experimental variable, unlike happy, sad, you have specific, you can create specific variables. In this case, people do call it inter-subject correlation. They just calculate it between subject 1 and subject 2, say the same brain location, see if they have some synchronization. So that's why it's called inter-subject correlation. So between any two subject pair, each subject pairs, two subjects, you calculate correlation between the same the location between the two subjects. So that's called inter-subject correlation. So that's a little bit challenging. That's because it's because of the structure of those correlation matrix. But I'm going to skip that part. So one problem with the typical fMRI data analysis is called the multiple testing correction. Why we have this problem? Well, remember the traditional statistic, we put it up as straw man. That straw man is called the null hypothesis. You pretend nothing going on in the brain, right? Now you build your model. When you have the model, you build, you pretend, you make, put it up as straw man. Then you say the model, how consistent your model with that null hypothesis. So that's the statistic value is used. In the end, you have that p-value, the magic p-value. If the magic p-value is less than 0.5, that magic number 0.05, then everybody loves that number 0.05 because then you can say something, you can publish the paper. That 0.5 is called a false positive because that's pretty much like what's going on in the court. Right? You have a trial. That's usually in the U.S. at least the judicial the system works we assume the person is under trial is innocent. That's like our null hypothesis, right? So that person is innocent. Now we go through provide evidence. And then in the end, the jury make a decision. The decision, there are two decisions, of course. So that's why we have this 2-by-2 structure. Is either innocent or guilty. But we don't know that ground truth. But for the jury, you have to make the decision, either reject the null hypothesis or accept the null hypothesis. So that's why we also end up with this type 1 error. So that's the worst case, right? So that's type 1 error. That's false positive. It's innocent, but the jury make a mistake. Say it's a guilty verdict. We want to avoid that part. That's pretty much like when we do science. We want to avoid nothing going on in the brain, but then in the end you say, I found this brain region is activated. That's the worst scenario. We want to avoid that. That's why this concept of a null hypothesis. That approach, there's an end up with this called type 1 error versus a type 2, right? So that basically this cartoon shows what is this false positive, right, versus this false negative. Those are two, how to differentiate the two type of mistakes when we make such a judgment. But the problem with brain fMRI data analysis, because we analyze each voxel separately, so that suddenly become a problem, because just by pure chance, if your p-value is 0.05, that's just for each voxel, that's the false positive rate. But we do that many, many times. How many times? Typically, for example, 100,000 voxels. We do that many, many times. Suddenly, that increases the false positive rate. That's why it's called multiple testing or multiple comparison. So how do we manage that problem? Because if we go through the algebra, that false positive rate increases a lot when you do that repeatedly. So the problem currently, people solve this problem, just pay the penalty, just lower the original p-value. So if you read the fMRI literature, there's a term called correct p-value. That phrase, correct p-value, basically says something about they want to handle this issue, but you pay the penalty. You pay the penalty, that's the problem. That's makes the life very hard. So especially when the small region like amygdala is very difficult to survive such a correction. So that's the main problem. So in the end, I want to summarize with the talk by mentioning a little bit the current problems with the current fMRI data analysis. The main problem is shared with the typical conventional statistic. This null hypothesis strategy is part of the problem. That's because nobody really cares about the null hypothesis, right? Everybody cares about it. There's an activation in the brain. We feel excited about it. But that's a little bit disconnection from what they are as an investigator, as a scientist. You don't care about null hypothesis. So that disconnection is the source of the problem. So that problem is basically in the end, we have this binary decision. Either you say this brain region is activated, or you can't say anything about the rest. But people tend to forget about that fact. You make that binary decision, this brain region is activated. Strictly speaking, you cannot say anything about the rest of the brain. They fail to survive your correction or your significance. That does not mean those regions are not activated. Simply, they fail to reach some threshold. Doesn't mean those regions are not activated. It's possible some of the regions are not activated. Most likely, some regions are activated, but they just fail to reach that threshold. So that's the source of the problem. Is there any way to solve that problem? Well, no magic solution, but at least probably there's a better approach. That is what I mentioned at the beginning, that Bayesian, that HIV test. that probably will, hopefully will give some better leverage. That's something probably in the future we should, at least that's one direction we could focus on to improve this p-values problem. So so with that, I think I'm done with this talk. Any questions? No? All right. Thank you.